first of all, I just posted the homework, so you can have a look at the homework. It's due Wednesday next week. There might be like some minor modifications because there's always mistakes in every homework I posted so far. So they might check updates of the PDF. It's posted on the class website. Give me 1 second. Also, is this recording? Yes, it's recording. So also, if you're still on the waiting list, it's very unlikely you're going to get into this class. So unless you're a DSI student or a PhD student. And so, but you can audit, and I already gave the courseworks to most of the people that sent me an email about auditing. So today, we're going to talk about version control and testing. So this is going to be basically all about just software infrastructure. There's going to be no machine learning today. Maybe on Wednesday we'll start machine learning. Maybe it's going to be only visualization. We'll see. So in the last couple of years, usually I did a very advanced version of Git, but I've realized that a lot of the people were not so familiar. So this year I tried to do a little bit of a more introduction to Git that's like maybe hopefully not as deep. If you know Git, it might be a little bit boring, but I want to catch everybody up. And so the reason I'm doing this in this machine learning lecture is because no one else does it. I think everybody in DS and CS should really know how these tools work because it's all about developing software. Unfortunately, no one else teaches it, which is why I'm doing it in this class, because I think it's really important if you want to be a data scientist in practice to know your tools well. So why do we care about, why is this broken? All right. So why do we care about version control? So here's a comic from PhD Comics, which is usually pretty great, about handing in a document to your advisor. And of course, once you wrote it, you're happy and say, oh, wow, this is final. And your advisor gives you some feedback, or maybe your reviewer, and it's final version 2. And then you get more comments and so on. And so you have incremental versions of your paper or report. And it's very hard to keep track of which version you're working on, and also to take parts of one version and put them into another version and see which changes were made why. This is true for writing, but it's even worse for code. In code, very often we need to make changes. We are fixing bugs. Maybe then we figure out, oh, the thing that we had in the first place was correct, so we want to go back to that. We want to make sure that there's no regression in performance or in the accuracy of our models. So it's very important to be able to compare different versions of the same code. And it's also very important to collaborate together. So you might know collaboration stuff from Google Docs, where you can do things simultaneously. Usually people are not simultaneously coding, but they're working on the same project. So my background is obviously working on scikit-learn, where there's like usually at least 100 people having proposed some changes simultaneously, and you need to synchronize them some way. And version control allows you to do that. So there's this very helpful version control flowchart here, whether you need version control. And yes, you do. And so you need to install Git. So I'll talk about Git and GitHub for most of the rest of today. There's 2 guides that I quite liked. Or the first one is general guides on GitHub. GitHub has a bunch of educational material, which is quite good. And below this is like a simple introduction to Git or something like that. There are also, the bottom one is linked in the syllabus. Maybe a quick round. Who here has used Git before? Okay, who here understands Git? Okay, 5 people, that's good. You know how rebase works? Anyway, So another comic I really like, XKCD. Maybe I'll give you a sec to read it. So basically everybody uses it, but no one really understands it. And the common method is, if you broke it some way, just delete the folder and start fresh. Obviously, that's not really great. Actually, while I really highly encourage everybody to use Git, I think it's really bad user interface. This is an old meme. I don't know if you get it, but so this is Linus Torvalds. Linus, who wrote the Linux kernel, also wrote Git to develop Linux kernel. He's really good at software engineering, not so good at user interfaces. The commands are really abstruse, I think, and it's really hard to understand what's going on. So Git is not really beginner-friendly, I would say, if you really want to understand what's going on. So I want to start today with like some beginner stuff, and then hopefully get into the more advanced stuff and more deeper understanding a little bit later. So first, if you start using Git, you first need to configure it. Usually you configure it once per machine that you're on. You can do this with git config, and you should have your name, your email. You usually want to set the colors to be auto, and you want to set your editor. The editor is used not actually for editing code, but it's used for editing commit messages and changing the history of things. I think by default it's Vim or VI. If you don't know VI, then change this to something else. I think the most common Stack Overflow question on VI is, how do I get out of VI? So if you don't know how to get out of VI, change this to something different. So Git has a bunch of really amazing properties. So let's start with, how can I set up a Git repository? So let's say you want to have a Git repository for your homework. Actually, don't do this for our homework. This is just an example. So Git tracks changes which are inside one folder and subfolders. So let's say I want to track a folder called homework1. So I make this folder, and to make it into a Git repository, the only thing I have to do is call git init, assuming I have Git installed, of course. And that tells me I initialized an empty Git repository in this folder. What this means is it just created this one subfolder .git, and this subfolder.git contains all of the version history of everything that you record within this homework1 folder. There's also, so there's no like database or anything like this backing this repository. It's all in this .git folder. So unless you back it up somewhere else, if you delete this .git folder, you make this folder into a plain old folder again. It's not a Git repository, and you lose all the information. Which is why it's good to back it up, say, on GitHub. All right, so one of the most important commands in Git is git status. Git status shows you the status of the repository. If you do this in an empty repository, it tells you you're on branch master, there's no commits, and there's nothing to commit. So this is sort of the standard way to create a repository from nothing. A much more common way to create a repository these days is by cloning it from GitHub. I'll talk a bit more about GitHub later, but just to illustrate how you get a repository there, this is how you probably actually will get your homework repository, is that you create a repository and then you clone it using git clone, and then this URL, that's, oh, I don't have a mouse here. If you click on the clone and download, it'll show you an URL here. There's two ways to specify this URL. One is with SSH, one is with HTTPS. If you haven't set an SSH key on GitHub, you need to use HTTPS, and you need to enter your password every time. I highly recommend, if you haven't already, deposit an SSH key at GitHub so you never have to enter your password again. Okay. Who here has an SSH key on GitHub? Okay. Well, that's good to see, but all of you should have it for the homework, because it makes working much, much easier. All right, so now we have a repository. What are we going to do with it? So the main workflow is that you have files in your working directory, which is here called, or also your visible file system. So this is just the folder you have on your disk. And you edit your files, you write code, you make the solution to your homework, and so on. Then you have the command git add, that adds whatever is in your folder or selective parts that you want to add to what's called the staging area or index. This is sort of an intermediate area where you accumulate all of the things that you want to store. And let's say you brought everything into like a consistent shape. Then you can make a snapshot of this, everything you put in the staging area. And this snapshot is called a commit, and which is labeled here as permanent storage or the repository. So this is stored by date author. There's a hash of the commit, so this makes this immutable. And so basically with the hash is the thing that uniquely identifies this content. And it also has a pointer to all of the history of what happened before. And it also has a message, a commit message that's attached to each commit, in which you can say, what is it that's in this commit. And so there's always sort of these two steps. There's adding things to the staging area or the index, and then creating a commit. The reason for these two steps is that sometimes you want to add multiple files at once. If you make a change in some code, usually the change is not restricted to a single file. So you want to add multiple files at once and then commit all of them together. This staging area lets you do that. You can actually also stage single lines. So if you added like a whole bunch of debug code with lots of print statements, because that's how you do that, right? And then there's like a single fix that you actually want to commit. You can disregard all your debugging code and just add the single line of fix and put it in the staging area and then commit it. Fun fact, this repository is actually what people now call a blockchain or ledger, only that it has been used in every company worldwide ever 5 years before people used the word blockchain. So if anyone tells you, oh, we're using blockchain, yeah, of course you are. Everybody is. This is blockchain. Anyway, it's a blockchain because each commit has a hash of its history. That's what makes it a blockchain, but doesn't really matter at all. So here's an example of how this would look like. So here I add a print statement, print hello world to the file task1. If I then do git status, it shows me again the status of my repository. There's nothing on branch master. There's no commits, but there's what it's called an untracked file, task1, and nothing added. But you can add the untracked file using git add. So now if I do git add, what happens is two things actually. Git add says, this file task1, I want to track the changes in it in the future. So now it's becoming a tracked file. It also adds the current content of task1 to the staging area. So now after I did this git add, I have all the content in task1, which is the single line. It's in the working tree, so it's in my file, but it's also in the staging area. And so if I then call git commit, and I can also specify a message directly. So here this message is say hello, -m gives the message. If I do this, then the content of the staging area will actually be stored in the commit. You can see the branch I'm on, which is master here, and you can see this is I think the first couple of entries of the hash, then the commit message, and it tells me one file was changed, one insertion, so that means I inserted one line, and the change was to create this file. If I want to see everything that happened in my repository so far, I can do git log. Git log shows me all the commits, who did them, when they happened, and the commit message. So here, this is the full hash of this commit. Here, this were only the first 7. And you can see I did this commit today at 12:37. Okay, so I was really prepared for this lecture, as you can see. So if you make more commits, you'll basically get a longer and longer list of these changes that are stacked on top of each other. if you want to view what the changes are directly, you can use git diff. Git diff shows you the lines that were changed. If you could git diff without anything else, it'll show you the changes between what's in your directory now and your last commit. If you do git diff -- staged, it shows you the changes between what's staged and the last commit. And if you do git diff and the hash, so the hash identifies a particular commit, like somewhere in the past, then it shows you the changes between what's in your folder now and what's in that commit. So a commit is uniquely identified by this really long hash. Usually you need to use the first 7 digits of the hash, or 7 characters of the hash. But it's still kind of hard to memorize. So there's different ways to reference different versions. The easiest one is the current version is always head, and then you can go back in time using tilde. So head ~1 is read as head -1, or then head -2 goes back 1 commit or 2 commits. So you can compare what's happening in the directory now to what was there before. Or you can use git log, look up the hash, and then compare to the hash. Okay, yeah. So git diff head -1 will be last commit, git diff head -2. This will be the changes between what was there 2 commits before and now, so it's all the changes in between. All right. So let's say now we have like a history of changes, and we want to go back to an old change. So let's say, okay, I made a new change. Instead of saying hello world, I say goodbye cruel world. So now my file task1 says goodbye cruel world. But then I realize that's way too dark, and so I want to go back to hello world. So git checkout task1 or git checkout head task1 means I'm going to go check out the version of task1, how it was as at head. Head is the last commit. So here, if I do this, the content of task1 will be changed to what it was during the last commit. So now it's hello world again. So let's say we did the same thing, but we already committed it. So I changed the line to goodbye cruel world, and I add it to the index, and then I do commit -m to make a commit. So now there's 2 commits. Unfortunately, it's like a little bit cut off. So below here, you can see there was the first commit, and then above it, there's the latest commit from 1244. The message is saying goodbye, and this is the hash. And so, but now, again, let's say I realize this is actually a bad commit. I don't want to do this. The way to go back is usually resetting. So you can do git reset --hard head -1. If I do that, head is now at 7139 FB, or the commit message will say hello. So this is how I basically discarded the second change. Later I'm going to talk about how to go back to this, but basically reset, there's several versions, but usually you want reset --hard, allows you to go back in time and make this what is your current files. All right, so far we talked about adding and committing. So now you're building up this commits built on top of each other, and we talked about with log, you can look at them. With checkout, you can get files back, or with reset, you can go back in time entirely. There's another important concept, which is branches. Branches allow you to work on different things at once. So usually each repository has a master branch, which is sort of, if you collaborate with people, this is the shared state. And then each person that works on it, or even by yourself, if you work on different things at the same time, each of them could be in a different branch, which is, in a sense, an alternate history. So I can make a new branch with git checkout -b and then the name of the branch. This checkout has nothing to do with the checkout before. It's just Linus like pulling on over on us. So checkout minus b creates a new branch. If you now make changes and add and commit and so on, you build on the history you had before, but you create a separate history, a separate branch of history. And I can move between branches by doing git checkout master. All the commits I do now are always added to the branch I'm currently on. So if I go back to master, I will not have the changes present that I did in new feature. In the end, and I'm going to talk about this later, usually you want to merge branches together. So that allows you, if you and your teammates worked on different things, in the end you want to put all of them together. You can do this locally, but you can also do this via GitHub, and I'm going to talk about the GitHub version in a little bit. All right. So next I want to talk about collaboration using Git and GitHub. So often there's like some confusion between what's the difference between Git and GitHub. So everything I talked about before was just Git, except for the cloning from GitHub, obviously. So Git is a distributed version control system. It allows you to do version control on your own hard disk. You can have a repository just in a folder and never show it to anyone. You can also have them in separate folders, and you can transfer stuff between folders if you want. Usually, if you want to collaborate, the easiest way to do this is to have a shared server somewhere, and everybody works on this shared server, and you have different branches, say, on this shared server. Git actually doesn't require this. With Git, you could work on a project together by handing around a USB stick, but it's a little bit annoying, so shared server is usually the best way. So what GitHub provides is two things. It provides a shared server, but on top of that, it also provides like some stuff for user management and for rights management, so that you can't like access my solutions, or your teammates can't overwrite your solutions and so on. And it has like lots of very nice UI features. For example, for code review and for issue tracking and so on. So you should think of GitHub first as like remote repository, so just as a hosted Git, but then on top of this, there's all these other tooling. So there's alternatives to GitHub. I don't have GitLab, but, well, there's GitLab, which is quite similar, but done by a different company. And there's Bitbucket, which is like not as nice, I think. And oh yeah, one thing you should keep in mind is that usually a lot of the stuff on GitHub is public, so everybody can see it. That it means everybody can copy it. It doesn't mean people can change it, though. For all your homeworks, please make them private. GitHub now has infinite private repositories for everybody, I think, because Microsoft is so generous. I don't know. So make all your homeworks private. And so here is sort of illustration using slightly different names from, let's say I have my homework locally and I add and commit things, then I can push them to the remote, and then they're stored on the server. And so push is the command you use to transfer all of the content back to the server. And pull is what you would use to synchronize the content of the server to your local repository. Yeah, okay. So if you only have your own repository, let's say your homework, the way this works is usually, as I said, so you clone it, as we saw before. You make changes locally. You push the changes. Let's say someone else made changes as well, or you go to a different computer and you can pull updated changes down. Pull is what you should use if you cloned the class slides, for example, because as you can see, I update them until 10 minutes before the lecture. So you can always pull the repositories. Will give you an updated version of what you cloned before. However, let's say you find one of many typos on these slides. Clearly, I don't want you to be able to push to my repository. So as I said, GitHub also provides write management, in particular, something called pull requests. So the way a pull request works is as following. It's one of the main features that are part of GitHub that are not in Git. So pull request is not a Git feature, it's a GitHub feature. So let's say you want to fix one of my typos. The way you do it is first you fork your repository. You fork my repository. That means still on GitHub you have a copy of my repository. This now belongs to you, so you can make changes. To make changes, you pull it to your local laptop. You make your changes. Then you can push it to your forked repository. So now it's on GitHub in your copy of the repository. And once this happens, there's a button that says create a new pull request. If you do the pull request, then I get a message saying, do you want to include these changes? This is great because it allows you to make changes to things you don't have write access to, like the slides. And so I highly encourage you to do that. It's also great because these pull requests have an interface for code reviews. If you're collaborating on something together, using pull requests is great even if you trust each other. So if I make a change to scikit-learn, it will always go through a pull request, even though I have the rights to push to scikit-learn directly. I don't want to do that because I can make a mistake. So by using a pull request, basically I show the changes to all the other people in the project, and they can look at them and they can say, okay, this looks okay. So on the first two homeworks, I think I'll have you work alone. In the later homeworks, I'll have you work in teams. And if you work in teams, I highly recommend you use pull requests as a method to do code review. Unfortunately, so I was thinking about including code review in this class, but it's way out of scope. And there's no other class in DSI teaching code review, which is really sad. But it's really important, and so I really want you to practice it by yourself. All right. So I hope this is somewhat clear. So now what happens if I updated the slides? So usually you fork a repository only once. And the fork takes the changes of the repository from the time it was forked. So now I upload the slides for Wednesday. And if you want the slides for Wednesday, you're not going to have them in your forked repository. The only way to get them is that you pull master from what is usually called the upstream repository. So you can pull the new slides to your laptop and then fix my typo, push it to your repository, and do a pull request. That's a little bit weird because it means that the master branch up here in your forked repository goes out of date, and there's no reason to ever update it. So this usually, you can push master there and you can update it, but there's no point. You will never ever use this, the master branch in your fork. But that's how GitHub works. But yeah, but don't be surprised if you pull from your own repository and you don't get the newest changes. Your fork will just go out of date, and you have to pull from the upstream. I'm not going to go through all of the commands here. You can easily look them up. Maybe I'm actually going to go through them. Let's see. But I don't think so. All right. So this is sort of the standard workflow I talked about, or these are all the things that are really important. So now I want to talk a little bit more about standard workflows and some tips on how to use Git effectively. So first, what will usually happen if you work on any project is you clone either your forked repository or the main repository. You branch. It's recommended you never do anything in the master branch. You always work in the feature branch. Maybe if you work alone on your homework, it's fine. If you work on a bigger project, never work in the master branch. So then you have these two steps of after every change you make, you add the change and you commit the change. You add the change, you commit the change, and so on. You possibly want to merge new changes from upstream. So if one of your buddies changed the repository, made some additions, you want to merge these things locally, and after you merge them, you can push your current changes back up. If you and your partner work on the same repository, and your partner pushes something up there, you will not be allowed to push as well, because that would override their changes. So if you both have changes, one of you will push first, and the second person that wants to push first has to pull down their changes, merge the changes, so unify them, and then you can push the unified changes that has everything. The merging is not done in the repository itself, or on GitHub. You have to do it yourself. Unless you use pull requests do the merge for you. All right, so couple more tips. So you should use git status all the time to see what's happening, particularly which branch you're on. I really highly recommend to install a plugin for whatever shell you're using that shows you which branch you're on and what's happening. So here I'm using ZSH, and so I'm using an extension called OhmyZSH, which is great. If you use ZSH, you should also use that. If you're using bash, use something for bash. And here you can see that in my command line, it shows me that I'm a branch master, and the red star means I have uncommitted changes here. And so it's really helpful to always see in which branch you're in. Git allows you to set the editor, as I said before, set it to something that you can use and exit. Allows you to set a pager, and most importantly, I think it allows you to set a diff tool. So if you want to do git diff, usually it shows it on the command line in a really ugly way. But you can also use nicer tools. I like Meld, which is like a Linux app. But I'm sure there's like great diff tools for all the other operating systems. Another thing that I find very helpful is using the git ignore file. If you have a file called .gitignore in your repository, everything that matches the content of gitignore will be ignored. It's like one thing per line, so there's usually many lines, and often you have something like .pyc, which are compiled Python files. You don't want to commit them, or cache Python files. You don't want to commit them, and so you put them in the git ignore, and they'll never show up in Git. Also, I imagine many of you use macOS. Is it called that yet? I think it's called that right now, right? I don't keep track. Anyway, each folder you have has a file called .ds_store, and it will ignore everybody that doesn't use macOS because it's littering it everywhere. And so you can put it to git ignore, and it's never going to show up.
So is git ignore like a text file?
It's a text file.
File name, so things won't do it.
Yes, and you can have file names or you can have patterns. So you can do star dot something, or you can just do dot something, but it's one per line. GitHub actually has like some pre-made ones. If you create a new repository in GitHub, you can say which language it is, and then it can add your git ignore for you. I should definitely have an example on the slide, but I don't. Oh, also the IPython notebook checkpoints you always want to ignore. So there's always .ipynb-checkpoints if you use Jupyter anywhere. And yeah, definitely ignore this always. This is a little bit small. So another thing is Git allows you to do aliases. When I showed you git log earlier, I actually didn't show you the standard log. I showed you some modified things. So this is the output you get here. Okay, I think this is actually from scikit-learn from 5 years ago or something when I first made these slides. So you can here see I use git log --one line --decorate --all --graph, and what it does is it puts a single commit on a single line. So there's the hash, then there's the commit message, and you can see it draws this graph. And so here you can see this thing has two children, this guy and this guy, and so these are different branches. So it kind of draws the branches. And you can do this on the command line with adog. So this one is graph. So usually you want all decorate one-line graph. The decorate tells you, maybe a little bit hard to see, but the decorate tells you where head is and where different branches are. So up here you can see there's head, master, upstream, and here there's like wrapper, give up, ignore alarm bar to diff errors. These are the branch names. And so you can show all of these by either aliasing. So usually I would just alias git log to this. I want to go ahead a little bit because there's another thing called git k. Git k is a GUI that comes with Git that it's basically very similar to git log, but it shows you a little bit nicer, not in the command line. So actually I use git k more often than git log. I also very often use git GUI. Git GUI is a GUI that comes with Git. It's not very pretty, but it's very useful. So this is for doing add and commit. So here you can stage things. So staging means adding to the staging area or to the index. And so here I can see on the left all the untracked files and all the files that are changed, and I can selectively choose which files I want to add and also which lines in the files I want to add. And so then the thing that's in the bottom left here is the staging area. So, and then on the bottom right, I can add a commit message and then click commit. So this is actually what I usually use. Different people have like different preferences. GitHub also has a UI you can use. I like this because it makes it very easy to select different lines and also see line by line what are the changes that I made. And it's usually installed with Git, so you can just do git GUI and it shows up. All right. Questions so far? No. Okay. Yes.
Why would you ever fork as opposed to when you just cloned the first time?
Sorry?
Why would you ever fork if you've cloned the repo initially?
Okay, the question is, why would I ever do a fork if I cloned the repo initially? So I need a fork if I want to do a pull request. So if let's say you want to change my slides, you pull my slides, you can clone my slides on your laptop. But then there's nowhere you can push them to because you don't have access to my, you don't have write access to my repo. You need to have a fork of my repo that you can push to on GitHub, and then you can do a pull request. If you never want to do a pull request, you don't need to fork it. Okay. So I now have like a couple more like diving deeper into Git things. Maybe just on a very high level, because we don't actually have as much time as I wanted to. The 5 things you should always think about when thinking about your Git repository is the working directory, which are the files that are right now on your disk. The repository, which is the commit graph in the history, which is usually like a big acyclic graph. The index, which is the staging area, which are the things that are going to be committed next. Which are where the branches are in this repository. A branch is basically just it's a tag that says where you are in the history. And where head is. Head relates what's currently in your working directory to the branches, or to the repository, sorry. And so I have this link up for Git for ages 4 and up, and it has like a Play-Doh representation for each of these, and little labels that physically represent these things. And if you think about what does a Git command do, think about it in terms of what does it do to these 5. And I want to talk about this somewhat briefly for some of the most common commits. And so what git add does, it takes things in your working directory and adds them to the staging area. If it's not tracked so far, it also adds them to the tracked files. That's pretty simple. Git commits everything in the working area to the repository, creates a new commit in the repository, so it's like a new node in the graph, and then it moves the pointer head that says, where am I in this graph, to this new node in the graph. Git checkout and then a branch name moves head to branch and changes the working directory to match what was in the branch. So basically, you just move everything there. If you do git checkout and then a file name, it does something completely different that makes no sense at all. And then the other ones I talked about before is git reset. All of them move head, so where you currently are, to a particular commit, and takes the current branch with it. So if you're on branch master and you see git reset and then a commit, that means your current so your head will be there, so this is where you're going to be, and also the master branch will be there. And then depending on whether you soft mix or hard, the working directory will also change or not. One thing that happens very often is that people do git checkout and then a commit. If you do git checkout and then a commit ID, you're in headless mode, which is very confusing. And if you're in headless mode, that means you're in no branch. That means your head, which says where you are currently, points somewhere in the graph, but the thing where you are in the graph has no name. The way to fix this is either to do git reset and go somewhere where there is a name, or you can do git checkout -b and give the thing a name where you currently are. So git checkout -b just says the thing where I am now, give it a branch name, also move head to this branch. Here's a nice representation of these. That also includes push and pull and fetch. So we saw before here, adds from the workspace to the index, commit goes from the index to the local repository, push goes from the local repository to the remote repository. Fetch, you can go from the remote repository to the local repository, or if you use pull, what it does basically is fetch and then a checkout or merge. Checkout and then a branch name goes from the local repository to the workspace, and checkout and then a file goes from the index. All right. I think I don't want to go over too much more. So I had a homework on rebase the last semesters, and everybody was very confused. I'm not going to do rebase anymore. If you want to know if you really want to be a good Git user, you should learn rebase. If you haven't used Git so far a lot, don't worry about it. We're not going to do it. The only other thing that I want to talk about in terms of Git is reflog. Git reflog is the secret to all the things that you lost. If you use something like reset or rebase, then you move your graph and you mess up your graph. And things that you had before might not be in your graph anymore. If I do reset head -1, I go back one commit. The commit that was there before is gone now. It's not in the graph anymore. And so if you want to go back to things that are not in the graph anymore, you can use reflog. And reflog has these things called where you can do head and then add in a number, not head tilde and then number. So these basically don't go back in the history of the graph, but it goes back in the history of the weird things you did with your head. The head pointer, I mean. So if you ever think you lost something irreparably, which usually happens, if you look at git ref log, you will probably see it show up there, and then you can go back to it.
Is the ref log stored in your local repo, or is it?
Yes, this is your local repo. If you also delete your .git file, you're lost. Don't delete your .git file ever. But and this only works for things you ever committed. So this is if you committed something and then lost this commit some way, because you rewrote your history in a weird way, then reflog can find it. If you never committed it, reflog cannot help you. So this is basically the attic of all the commits you ever made, but that got lost somewhere. So yeah, if you're already a little bit familiar with Git, I recommend you watch this Git for Ages 4 and Up with Plato. If you're not, there's an introductory to Git slide deck that I linked to in the materials. So this one I actually think is a little bit more advanced because it talks a lot about branching and so on, which might not be that important in the beginning. Any more questions about Git? Okay, I think I answered the question of why is it so hard and strange in the beginning. So, all right, the next thing I want to talk about is unit tests and integration tests. So this is about software testing. Okay, who here has written a unit test before? Okay, so this is shockingly few. Who here has written a unit test and it's not in the computer science department? Oh, very good. Well, so if someone is serious about writing any software at all, everything you write in your software should be tested. And by tested, I don't mean you tried it out. By tested, I mean there should be an automatic test. There should be a script that tests that the program is working correctly. If you wrote software and there's no test for it, you definitely need to assume it's broken. If you tested for it, then you know at least the parts that you tested for are not broken. At least this very specific scenario you tested for are not broken. You should treat any software that's not tested as broken always. So I see a lot of more people of you used Git than wrote a test, so assume that everything you ever wrote was broken. So why should you do this? So A, it ensures that your code works correctly. B, it ensures that if you change something, you didn't break what worked before. That makes actually writing code much easier because if you tested everything, if I make a change and I'm unsure if the change was good or bad, I make the change, I run the test. If the tests pass, it's pretty likely that either my change was good or my tests are bad. There's also something called regression tests, which are every time you find a bug, you add a test that says, does this bug happen? And so once you fix the bug, often it's easy to reintroduce the bug later on. Particularly if the person that found and fixed the bug is no longer at the company, someone later on might reintroduce the same bug. So you can add a test whether the bug happens or not. This is well, yeah, you can also use it to test edge cases and weird inputs. And you can also use it to ensure that your code is reachable. If you cannot, usually most tests have like some way to compute coverage, which says which parts of the code are hit by the tests. If you can't write a test that hits a particular part of your code, why do you need that part of the code? You should be able to come up with a scenario that hits that part of the code. If not, it's probably useless or you don't understand what's happening well enough. This is actually something that arguably testing is more important for interpreted and dynamically typed languages because the compiler can't check as much. So in Python, you can have like invalid syntax lying around and it's going to execute part of your code, but another part is complete garbage. I would argue that even if you write Haskell, you still need tests, because still you need to test for functionality. You might need a couple more tests if you write Python, possibly. So for most of your homeworks, I don't expect you to write tests, because it's actually very hard to do this for machine learning problems or for data analysis pipelines. If you write any software ever in your job, make sure you test everything, always. And I'll have you write some tests that are like very small, like toy examples, as part of the first homework. Some people take this testing to an extreme, I would say, and use test-driven development. It's one of many like development approaches and philosophies. In test-driven development, you write the tests before you write the implementation. So before you write a function, you say, oh, I want my function to do this and this, so I write a test that ensures this happens. And then I start implementing the function, and once the test passes, I know I'm finished. This is a pretty extreme way to do testing, and it definitely has its benefits. It's not something I do myself, because usually there's a lot of experimentation about the interfaces and so on. And for test-driven development, you have to think about, well, you have to settle on the interface first. Also, for like data science, I do a lot of data sciencey stuff, and there writing the right test is really hard, because you don't know like how accurate your model is going to be. So there's generally 3 types of tests that people use. Unit tests are usually for a very small unit of code, like a function. So that would be for like a very small, or the smallest possible piece. Check it does the right thing. Integration tests are showing that the system works and the whole process does the right thing. So let's say from reading the data to your prediction, whereas the unit test might be it parses the data correctly. And as I said, there's non-regression tests, which test that a bug got removed and it will not be reintroduced. Actually, this is a place where I often use test-driven development. So if I know there's a bug, I write a test for the bug, and then I work on the code until the test passes. So that's the case where I use test-driven development, where I write the test first. Because I know what's supposed to happen, I know it's not happening, that's the bug. So I write a test case for that, and I go debugging from there. Oh, actually another reason why you'd want testing is that it is a way to document what your expected behavior is. So you should also document your expected behavior in the documentation, but also you can make it very explicit. Let's say you have a function and its input at 0 is not really well defined because of some math. And so, like the area under the curve for something that only has true positives, whatever. If you write a test that ensures the value for 0 is a specific thing, then whoever reads this code will know this is what happens if I put in 0. And they also know you did it on purpose because you made sure it happened. If you don't document it and don't test it, then people might think it was an accident. You did it this way and it's a bug, or you should actually do it a different way. So it's a way to tell all the other developers and all your users and everybody who reads the code, I actually did this on purpose and this is the result I expect. All right, so how are we going to test? So in the course we're going to use pytest, and it's actually what basically everybody now uses for Python testing. There used to be a thing called nose, but no one uses nose anymore, hopefully. And basically what it does is it searches for all files that are called test something.py and runs all methods that are called test. And then it reports some nice error messages. And if you're really interested in messing around with the Python AST, you can read what pytest does behind the scenes. It does really crazy stuff to create nice error messages. All right. So here's an example of how this will look like. So here, for simplicity, I have both the function and the test for a function in the same code. Usually, I would have the test separated from all the implementation. So I would have a file with the implementation and a file with the test that's separate from it. Here, I put them both basically in the same thing. So let's say I have a function called inc that is supposed to increment by 1. What it actually does is it increments by 2. And then I have a function that's called testAnswer, which checks that increment of 3 is 4. So because we assume inc does increments by 1, and so we assume increment of 3 should be 4. And so in pytest, you usually you use the statement assert to assert something is true. Assert is a standard part of Python, and it just usually it raises an assertion error. So if you in Python, you would write just assert 5 equal 4. It would say assertion error false. If you do it in pytest, because pytest is crazy, so I do pytest. Actually, I think the dot is not there anymore. It's just pytest now. Pytest test sample. Then it starts. It says it's testing this file, and there's a failure. And the failure is in the function test answers. And it is in this line, assert inc 3 equal 4, where the assert is 5 equal 4, where 5 is inc 3. So you can see it actually, like, it clearly did something crazy to get this, but it gives you a very useful answer, which says 5 is not equal to 4, and you told me inc 3 is going to be equal to 4. And so now I can go back and fix the code. I can do change inc to return x plus 1. Then I run pytest again, and now it says 1 test passed in 0 seconds.
So we should always include our tests in the same file as all our methods?
No, sorry. You should never do that. So I did it because I want to put both on the same slide. Actually, what you should do is what's on the next slide. Maybe I should add comments to the other one. I didn't want to make it too complicated. So usually you have different files. So here, usually you have a file with the implementation and a file with the tests. And so in particular, you might not want to distribute the tests. Usually it's actually a good idea to distribute the tests to whoever uses your library or whatever. But usually you want to have them separate. And so also it's clear if you make a change, is a change to the code or to the tests? Because it's actually quite different. If you have a change, it's only to the code and not to the tests. That means you didn't test your change, and it was bad. Never have a change to your code, not to your tests. If you change your tests and not the code, it's maybe fine because you added additional test. If you change an existing test, that's also really weird, because it means behavior changed, and it shouldn't happen. Anyway, so here's a slightly more realistic example of, so you have one file that's inc.py and one file called testinc.py. So the test file, as I said, they always start with test underscore, or that's the default, that's what pytest looks for. Now if I run pytest in this folder, it will tell me 1 passed in 0.01 seconds. And you can see the passing tests are this dot here. So in testinc, so it saw this file, but it's not called test, so it kind of ignores it. And it saw this file, it's called test, and it has a function called test in it. And so it runs this, and the dot means the test passed. Great. But what I can do now is I can look at test coverage. And, actually, so here, in my implementation, I have 2 functions. One says that if x is smaller than 0, I return 0. And I have also a dec function which does a decrement by 1. And so in my test, clearly I only tested the increment function, not the decrement function. And I also, because I called it on 3, I didn't test the return statement here. So this wasn't tested, and this wasn't tested at all. So if I do pytest-cuf inc, So that means check the coverage of the inc file or the inc module. It tells me there are 6 statements. 1, 2, 3, 4, 5, 6. And it missed 2, which is actually this one and this one. I can also get a coverage report in HTML, which is a little bit nicer and I can look at. So if I do --cov report equal to HTML, it's going to generate an HTML file, which is going to have this and this. So there are multiple HTML files. There's going to be an index here for all the files in the module. I can click on this, then I can see this is the coverage. And so here it sees these lines are run. These lines are not run. So the def deck is actually run because the definition of the function is run, but the function body itself is never run. And so this basically tells me that I didn't do a good job writing tests. And in particular, it tells me that even in this function I tested, there's lines that I didn't test. This is super useful if you have complex workflows. If you have like some very complicated data processing pipeline with lots of ifs and like what happens to the content of your CSV file, you can see which things are actually used and which are not used. Questions?
So are you aiming for 100% coverage of everything all the time?
The question is, are you aiming for 100% coverage all the time? And that's a good philosophical question. And so scikit-learn doesn't have 100%, and most libraries don't have 100% for various reasons. Possible, like, I think you should always aim for 100%, and only don't test something if there's a reason not to test it. If you have numerical instabilities in the algorithm, actually, like in scikit-learn, there's like edge cases that are very hard to test because it happens only on very specific data sets or very large data sets. And we don't want the tests to run 20 minutes, but if you don't run it for 20 minutes, the numerical issue won't show up. Also, sometimes maybe you're lazy and you don't want to test certain error messages, like input validation things. We actually had bugs in our error messages in scikit-learn, so maybe do still test your error messages.
So in the data science workflow, are tests usually used in just the AFP process?
You should use tests everywhere. The thing is, it depends a little bit about what your data science workflow is. So if you're still in Jupyter, you probably don't want to write tests. And probably a lot of the stuff that you're doing is in Jupyter. Actually, all the homeworks starting next week, maybe, are going to be all in Jupyter. So they're actually going to be before the stage where you would start writing tests. And once you go to Python files with functions, which you should actually do as soon as you can, then you can write tests. And you should write tests for every function. And even if you write a test that your model is like 67% accurate because that's what it was yesterday, that's helpful because if you change something somewhere that you thought had no effect, you can see if it has an effect or not. And it's good to break up your stuff into separate functions so you can test these functions independently. Often your whole pipeline process is very complex, but particular parts are quite simple, like deal with missing values. You can write a function that deals with missing values, and you can test, did it deal with the missing values? And you can test it on the different special cases that you care about.
So does the number of statements that's done, does it include the first line of every function that each function?
Yes.
Even if it was not referred by the first line?
So, okay, the question here is, did it include this? Yes, because what this line says, this line defines the function. And the thing that defines the function was run, because the function is available. The content of the function was not run. So this Python statement here was run that defines the name deck. But yeah, it's like, you need to think about it for a second, but then it makes sense. All right. The next thing I want to talk about, this will actually also Wow, I have 10 more slides. It's going to be quick. This will be part of the homework, is continuous integration. And I used to use this for all the homeworks, but it's too much trouble, but we're going to use it for the first homework. So this is how you usually run tests, which is whenever you make a commit in your version control system, you have a bot run all your tests. And why do you do this? So basically, you run a fixed command for each commit or for each pull request. And usually, you do both unit testing and integration testing. You can use this for many things, like for building documentation or building binaries or whatever. And it has so many benefits. So one benefit is you never forget to run the tests because they always run automatically. If someone else changes your code and there's a pull request, the tests run on it, and if it breaks, you can tell them you broke the tests. What also is great is it requires a very clear declaration of your dependencies. If you run your data science workflow on your machine and everything works, you have no idea why it worked, basically. You might require libraries that you didn't even think about you're requiring. And so by running it on, so this continuous integration is run by some cloud provider on some virtual machine. So you need to tell the cloud provider exactly what you want in your virtual machine, and that specifies the environment that you need for whatever code you're running. And so this requires you to have this specification. If you don't do this, no one ever writes a specification of what they actually needed to run a given pipeline, unless they really have to. And so if you don't do this and you give your library to your friend, it's never going to run because you forgot something. Like some version dependency, like you need this version of pandas, or you need to have this obscure library installed, something like that. Also, you can build against different systems. So it's called a build matrix. So you can check, does it work on Python 2 and Python 3, on this NumPy, on OS X, and on Windows. And that's maybe not something you care that much about for your homework, but it might be actually if your boss runs Windows and you run OS X, you might care it runs on your boss's computer. And generally, if you have a heterogeneous environment, you want to make sure it runs like on your deploy server and it runs on your laptop or something like that. Certain servers, as I said, there's Travis, Jenkins, Circle. Travis and Circle are sort of two cloud provider. Jenkins is actually an open source project that's also has a hosted version. There's also Azure Pipelines now that Microsoft launched like a month ago. I haven't tried that yet, but they give you like lots of free credits. For the class, we're going to use Travis. And so in the homework, you're required to set up Travis. Oh, I already ran through benefits, but two that I forgot is it provides you immediate feedback. So if someone breaks your code in the pull request, it's going to tell them. You don't need to actually go in there and tell them you broke the code. These continuous integration servers are integrated with GitHub. And so if you break the tests, GitHub will give you like a red X, and it tells you you broke it. And so that gives you immediate feedback. So very briefly, how does it work? So it's usually triggered at each commit or push. It sets up a virtual machine of your specification. It pulls the current branch, and then it runs a command. Usually the command is install and then test. Or if you don't have like anything to install, if it's just a bunch of Python files, you would just run pytest. And then if pytest succeeds, basically this is sent back to GitHub, and you get a green check mark. If pytest fails, you get a red X. You can run many other things, like you can check for style, or you could check if your homework's correct. That's actually what a lot of people are doing, is using these for checking correctness. We're not going to do that. I would just want you to write tests and make sure your tests pass. Let me double check. Oh, we're nearly done. Cool. So what you need to do is you probably need to create an account on Travis CI Actually, here the URL is the URL from 2 years ago and shouldn't be this. But the correct link is in the homework description. So you need to go to Travis CI and you need to flip a switch that says, after you created your homework repository, you want to run Travis CI on it. So the way your homework repositories will be created is via GitHub Classroom. So you should have all gotten an invitation to GitHub Classroom, or you're going to get it today, I think. This invitation gets a link. This link will create a new repository for you. And you're going to clone this repository and work in this repository. And you're going to set up Travis to run on that repository. So for that repository, you will have to go on Travis CI and click on this thing and turn it on. You also need to specify a Travis YAML file, which basically has to say what is the environment, what should be installed, and what should be run. And so it should look something like this. I only required you to have Python 3.6 and 3.7 in the language. Then with pip install, you can say all the dependencies you have. I think the homework, the tests don't have any. Oh, they have probably pandas as dependencies, so you need to install pandas. You can also just do pip install pandas. And then the script, which is what it should do for the tests. So you have to add this to your repository, flip the switch, and then continuous integration should run on Travis. And you will see the output on Travis. As I said, we're not going to use this for the rest of the semester because it turned out that it's too much of a hassle because of the way GitHub Classroom is set up. If I see any library and it doesn't have this set up, I stop looking at it immediately. If you have ever any project that you want anyone else to look at it, have continuous integration for it. If you're going to work at a company, most companies have their own internal system that is like Travis CI. So it will be slightly different, but in a sense it will be the same. Like Google, Amazon, Facebook, they all have the same thing internally. If you're at a startup, they're probably going to use Travis. One second. Usually what you will also see is continuous deployment. So, which means once the test passed, you actually want to put this on a production system. So we don't do this here because it would be kind of out of scope, but actually in very high-end real-world systems, there's if you make a change, usually it means your machine learning system will be retrained, and then it will run through the tests. If the tests pass, it will be deployed. So there's a whole pipeline of each commit triggers a retrain, triggers a test, triggers a deployment.
Quick question. In the homework one, there's already a link to GitHub Classrooms. Should we use that one, or should we wait until we get an email invitation?
Oh, the question is, in the homework one, there's a link to GitHub Classroom. Should we use that? Yes, you should use that. Sorry. You all got the invite for, you actually all added to GitHub Classroom. Sorry, I confused that. You're not added to Gradescope yet. You have to submit your homework both on Gradescope and GitHub Classroom. The GitHub Classroom will basically be automatic, so you get the repository from there, and you just put all your stuff in this repository, and then you push it, and the repository will just close at the deadline. And we'll use this system all the time. And for the Gradescope, this is where the grading will actually happen. You have to upload your code to Gradescope. We use these two systems because on GitHub Classroom, for the next exercises, I'll keep you Jupyter notebooks, and on Gradescope, I'll have you submit PDF files that are rendered. So that's why you'll have different things for future homework on the two. For the first homework, you'll have the same code uploaded both to GitHub Classroom and to Gradescope. Other questions? Okay. That's it. So homeworks are out, due next Wednesday. If you have any questions, please ask them on Piazza, because if you have the question, someone else will have the same question.